So let's talk about kinetic energy again. Remember, when we have an object moving with speed v, we define the kinetic energy of the object as a scalar quantity 1/2 mv squared. This is scalar, and what's very important to realize, it is reference frame dependent, because the velocity of the object depends on what reference frame we're in. Now, one thing to keep in mind is that, remember our definition of scalar product. A dot b is the magnitude of A, the magnitude of b times cosine of theta. So a vector dotted into itself is just the magnitude of A squared, which we can just write as A squared because the angle is 0. So here we have a v squared. So the dot product v dot v, v squared, enables us to write kinetic energy as 1/2 m v dot v. And we see our first example of a scalar product describing a physical quantity. Now, if we had a coordinate system where we wrote v as vx I hat plus vy j hat plus vz k hat, and we took the dot product of that vector with itself, then we just know that it's the square of the components. And so in a Cartesian system, we can now say that the kinetic energy is 1/2 m vx squared plus vy squared plus vz squared, because that's the velocity squared. So there's a simple way to express abstractly the kinetic energy as a dot product, and explicitly in a coordinate system as the sum of the squares of the components of the velocity. So far, we've defined work in one dimension, but let's consider the path of a particle in more than one dimension. And on this screen, it looks like a two-dimensional path. And here's our particle. And what we'd like to do is define the concept of work for this type of path. Now, let's say that at this instant, our particle is experiencing a force F. And the particle is being displaced by a distance ds, which is always tangent to the path. And what we'd like to do now is talk about the work done for this particle. Now, what we'd like to first say is, what we're going to do is imagine that we're going to break the path down into a bunch of small intervals. And let's call this the jth point and the jth plus 1 point. Then our particle will start at j, and we'll displace it delta Sj to the jth plus 1 position on the path. And here, let's denote the force by Fj. And now what we'd like to do is define the work for this particular section. Now, our concept of work is the force in the direction of the displacement. So what I'd like to do is I'd like to define the quantity Fj, and I'll put a little parentheses upstairs, parallel lines upstairs. This is the component of the force Fj in the direction of delta Sj. Now, the way we denote that is we can then say that if I take the dot product of Fj dot delta Sj, this is the component of the force in the direction of the motion, because remember our dot product, if we call this angle theta j, is taking how much of one vector is in the direction of the other times the magnitude of that displacement. And again, when we write that component in our notation, if we call this angle theta j, we know that that's the magnitude of Fj times cosine of theta j. Now, because this is the amount of force in the direction of the motion, that's how we've defined work done. And we'll symbolize the work done in taking the particle from j to j plus 1 by the symbol wj. And now, this is a scalar quantity. And when we want to find the total work, what we have to add up is from some initial point to some final point, how much work is being done in taking our particle from the initial position to the final position. And it's just the sum for all of these j's, and let's say we have n of them, of wj. And right now we're going to call this w, is just that scalar sum. And that's equal to the sum, j goes from 1 to n, of fj dot delta sj. So now we'll use the vector dot product because we already know that this is how much of the force is in the direction of the motion. However, this answer depends on how fine we broke up this path. And what we've seen many times now is that the actual work that we want, let's write this as n because it depends on the number of paths, is the limit as n goes to infinity of this sum of scalar amounts of work. Now, when we take that limit as n goes to infinity of this sum, j equals 1 to n, of fj dot delta sj, this quantity is formally what we mean by a line integral. And we denote that with a new notation. We'll denote a line from our initial to final. And it's a dot product of the force dotted into the small displacement. Now, whenever we see the dot product in an integral, that distinguishes it from a normal integral, and this is what we call a line integral. Now, again, why did we switch from our delta s's to ds's? Because when we take the limit as n goes to infinity, our grid becomes finer and finer and finer until we're shrinking down to a point where we can just talk about the differential displacement ds and the force acting on a point. And that's what our line integral is. Now, what we'll learn next is how to calculate this line integral for a number of important physical examples that occur in our interest in mechanics. We would now like to generalize the work-energy theorem to more than one dimension. Remember that we defined our work as an integral from a to b of a force dot ds. And graphically, let's look at that as if we start at A and we go to a point B, and if at some point on this path we have a force F, and the displacement is always tangent to the force for an object M, we would like to now figure out how this integral is related to the change in kinetic energy. So first off, it's always important when analyzing a new result to understand where Newton's second law comes in. And for our point particle, Newton's second law is that the force is equal to ma, which we can write as mass times the derivative of the velocity. And so our first step is to rewrite the work integral, and now to incorporate Newton's second law into this integral. So this is no longer simply a concept of physics, but it's combining the second law and our definition of work. Now, what I'd like to do here is to note that the displacement of a particle is always equal to the velocity times dt. So if we put that result in here, ab of m dv dt dot v dt, you can see that we can cancel dt's, which is essentially taking the time out of this integral and writing the work entirely in terms of the small change in velocity dv scalar product with the velocity. And this is the quantity we'd now like to calculate. So one way when we ever want to calculate these dot products, we choose a coordinate system. So let's choose a Cartesian coordinate system plus x plus y with our unit vectors I hat and j hat. And now our task is to write down these various vectors. So for instance, dv can be written as dvx I hat plus dvy j hat. Now, if we were to go into 3 dimensions, we would have dvz k hat, but I'm just going to do this in 2 dimensions. Similarly, the velocity is vx I hat plus vy j hat. And now when we take the dot product, as we've learned in Cartesian coordinates, it's just the components dvx, vx, and I'll just do a little parentheses there, plus dvy, vy. And so now our work integral, AB, is equal to the mass times dvx, vx, plus the mass times dvy, vy. Now, what we have here is a sum in the integrand. But by the rules of integration, we can rewrite this integral as two separate integrals from a to b of m dvx, vx, and from a to b of m dvy, vy. And now we can integrate each of these separately. And if you recall, in one dimension, we used our integral formula. This is just vx squared. And when we integrate them, what we have to look at is the endpoints of our integral. What we're integrating is the velocity, and we're going from some initial value to some final value. So our first integral simply becomes m vx final squared. I'll pull out the factor 2 minus vx initial squared, where a vx initial is the initial x component of velocity at a, and vx final is the final component at b. And I have a similar term here, which is vy final squared minus vy initial squared. And when I combine our terms, vx final squared plus vy final squared minus 1/2 m vx initial squared plus vy initial squared, we've already shown that our kinetic energy, 1/2 m v dot b, is 1/2 m vx squared plus vy squared. And so we see that this is just the final kinetic energy minus the initial kinetic energy. And so we can call that delta K. And what we have now is the work energy theorem. And I'll come back to my original statement that the work is equal to the change in kinetic energy. And this is a combination of our definition of work and Newton's second law. Let's apply the work energy theorem principle to the motion of a block sliding down an inclined plane. And here's an inclined plane at an angle theta. And let's choose a coordinate system. We'll choose x equals 0 up here, I hat here, and here is our coordinate function. And suppose that the object starts at xi and it ends at x final. If we want to calculate the work energy, then what we're going to learn is that this theorem is two different sides. Calculating the change in kinetic energy is simply a description. This is 1/2 m v final squared minus 1/2 v initial squared. That's a property, parameters of the system at the initial state, the speed, or the velocity speed, which is kinetic speed squared, and the same property v final in the final state. Now over here, we have two types of forces acting on this object. So here, we need a free body force diagram first. And this side is where the physics lie. And so we want to draw our force diagram. So if we have our block, we have the friction force, we have the normal force, we have mg. Recall, if the plane is inclined theta, that's also the angle theta. If we chose I hat, j hat unit vectors, I just want to repeat that on my free body diagram. Now, we can think of this integral as just one-dimensional motion in the x direction. And so we have two different forces that we have to calculate. The friction force is in the minus x direction, so we're integrating minus the friction force with respect to displacement from x initial to x final. And what about the gravitational force? Well, the gravitational force has a component mg sine theta in the x direction. So when we integrate that x component, we have now plus, because it's in the same direction. Remember, we're displacing a little bit dx down the inclined plane, so we're going from x initial, x final of mg sine theta, which is a constant, dx. And so when you're applying the work-energy theorem, you need to integrate your forces and actually calculate the work. Now, again, if you looked in the j hat direction and we applied Newton's second law, n minus mg cosine theta is 0, and our rule for friction is it's mu k times n, or mu k mg cosine theta, then what we have is that in both instances we have a constant force, so it's just force times displacement. So we have minus mu k mg cosine theta times the displacement, which is x initial, x final. Over here we have mg sine theta times x final minus x initial. And now we've calculated separately both sides of our work kinetic energy principle. As in all our physical laws, the equal sign means the work is equal to the change in kinetic energy. I'll emphasize that by now placing the equal sign because of our physical law. And so equaling 1/2 m v final squared minus v initial squared. And now I have a relationship between the parameters of the initial state, which I'm calling x initial and v initial, and the parameters that describe the final state, x final, v final. And depending on which set of these parameters are given, I can conceivably solve for the other ones. One thing I do want to point out when we do this example is we've described work as a dot product from A to B. Take the friction force. Well, in this instance, if we wrote this out explicitly, it would be minus fk I hat dot dx I hat from the initial to the final. I hat dot I hat is 1, and so you see we recover from x initial to x final of fk dx. And that was the first piece. The second piece, the gravitational force dotted into ds from x initial to x final. Well, if you wrote down the gravitational force, mg, as a I hat component and a negative mg cosine theta j hat component, then when we take the dot product, again, where our ds here, we'll write ds as dx I hat, then when you dot product mg dot ds, mg dot ds, we have I hat dot I hat, which is 1. But j hat dot I hat, they're perpendicular, so that's 0. So the only piece that survives in the scalar product, mg dot ds, is these two pieces. And so we get the integral from x initial to x final of mg sine theta times dx. And that's precisely our second piece here. So here's the simple application of the work energy theorem.